Okay, we are on Unit 9 once again on the refrigerant oil chemistry and management. These are the pictures that accompany the previous PowerPoint slide presentation. This particular illustration here, I believe, is on page 244 of your text. And what we're showing here is how the hoses and everything are connected to this system. Notice this is a huge recovery machine here. Notice that you're going to have a, this is your recovery unit. It includes a sight glass. It shows how the hoses are hooked up. This is the refrigeration system that is being recovered in the form of refrigerant. Now, what happens here is on this particular system, this shows how the hoses are all hooked up. And here's the scale showing the bottle that the refrigerant from this system is recovered to. Remember, we're going to fill this thing to 80%. And this cylinder typically could be a 30-pound. It could be a 50-pound, or it could be a 100-pound cylinder, depending on how much refrigerant we're recovering from the system. In this case here, we have a reciprocating compressor, and we have a purge valve for the recovery unit, as well as the oil drain valve to take and remove oil that has come out of the refrigerant through a separation process inside this recovery machine. This is an air-cooled machine, and I will tell you this just from doing recovery in the past. Basically, what happens here is over a period of time, the bottle will get hot. Now, how do you keep that bottle active in the way of recovering refrigerant? Is you take and put an ice bath around it. What I have done is I've taken the recovery bottle and I've put it in a bucket of ice in order to cool it down. When you cool down the recovery bottle, the hot liquid refrigerant now cools down, lowering the pressure temperature, and it also increases the recovery rate. So typically what we're doing here is, in this case, we are actually pulling out of the liquid side instead, the high side of the system, which contains liquid refrigerant, through this machine, and we are recovering liquid refrigerant into the cylinder. Okay, these are serial plates that you're going to find on compressors with the barcodes. Are going to tell you, it's going to give you the model serial number. It'll also tell you what type of oil this thing is charged with. It'll also tell you what type of refrigerant that is in the system. These are, if you look at these right here, if you take and look at these right here, you're going to see that you have, this is off a Tecumseh Compressor, okay, a Tecumseh Compressor, which is, this is an AE family, and this is going to tell you, in this case, this particular compressor is compatible with R290. This particular compressor over here is compatible with 134 alpha, so forth and so on. And this gives you an application telling you the date code of the compressor, etc. Okay, this is the chlorine atom. I should say these are basically showing you the, it's going to show you the chemical composition of HFCs versus HFOs. And I believe, give me a minute, you can find those on page . Okay, this here is going to be found on page 222. This is figure 9.7. Basically, this is at the bottom of the page. These are HFC molecules, which only have a single atomic blend, while the HFO refrigerant molecules have at least one double atomic bond. This is just the chemical composition of HFOs versus HFC refrigerants. Here we have another illustration here, R134A, and this shows the, let's take a look at this. Having a little bit of trouble finding this here. There we go. Okay, this is found on page 228 of your workbook, and this is the 134A and the 134A isomers, and just gives you the chemical makeup of this particular refrigerant. Okay, here we have a chart that basically shows the behavior of the azeotropic refrigerant blends. So if you look at this right over here, you're going to find this chart on page 229 of your textbook under Unit 9. Basically, you're going to see the subcool section right here between 3 and 4, your saturation level between 5 and 6, superheated level between 1 and 2. And basically, your temperature is going to be illustrated on this side. Over here on this same page, figure 9.13, this is a graphic illustration of the behavior of near azeotropic refrigerant blends. Notice that you're going to have A and B over here. You have two refrigerants here, right over here. Refrigerant 1, refrigerant 2, and basically you got your pressure drop here and your temperature on this side right here. Okay, here's another illustration showing the recovery process. Notice that if you look at this, utilizing this recovery machine, they are showing the sight glass, which is up here on the refrigeration system. And basically they're showing, I believe this is utilizing this recovery machine in order to take and push refrigerant through. Okay, basically this is referred to, if we're looking at this illustration, it's on page 243 of your text. And this is what they call the push-pull method of pushing out the liquid refrigerant to a vapor state when it reaches the system. So by you hooking this system up this way, you have the ability to just take and push a small amount of liquid through the system, and by doing that you speed up the recovery process. This is a little bit more involved. Every manufacturer does it a little bit differently. I personally don't utilize this method because most of the systems I work on are typically going to be smaller systems, typically 15 pounds or less of refrigerant, and I will utilize a straight recovery, vapor followed by liquid, and the machine that I utilize accomplishes that task within 30 to 35 minutes on average for a residential or a small commercial system. And I found this works extremely well. Okay, here we have a temperature chart, temperature pressure chart. I will refer to the page where you can find this in your text. But basically what we're going to be doing here, let's see here. Give me a second. This is found on page 231 of your text on Unit 9. This is figure 9.1, figure 9.15, again on page 231 of your textbook. And this is the pressure temperature comparison of R410A with R22. So you're going to see some huge differences here. Look what the temperature, typically 40 degrees, which is the design of the evaporator coil. Look what R410A pencils in at 118.2, versus 68.5. Huge difference here, guys. And if you look at the condensing temperature of 100 degrees, as a matter of fact, now you're up to 317 versus 195. So typically we say that R410A is 1 1/2 times higher pressure than R22, which it replaced. And down here, of course, you have a chart which basically shows the pressure temperature relationship between R22 as well as 410A. Here we have a chart, and this is going to be on the oil. Basically, this is going to be found on page 236. And on page 236, you're going to see the POE versus the mineral oil. What we're worried about here, this is the moisture absorbing capability of mineral oil versus polyester lube. Now, if you'll notice that the mineral oil is flatline. We're not so concerned about mineral oil in compressors absorbing moisture from the outside. POE oil is a completely different equation. If you purchase POE oil, you're never going to find it in a plastic bottle. It's always going to be in a metal can, and you cannot leave it open more than 20 minutes to 30 minutes maximum. If you do, that whole can is contaminated with moisture, and that oil has to be disposed of. So how do you get the moisture out of POE oil? There's only one way to do it, gentlemen, is you've got to use a filter dryer every time you take and install a new system, a replacement system, et cetera, et cetera, et cetera. So basically, anytime you change out a compressor, anytime you change out a evaporator coil, if you install new equipment, you must put a filter dryer on the liquid line. That is the only way you're going to get the moisture out of the system and out of the oil in the compressor. Now, if you think you can evacuate the system low enough to take and boil the moisture out of the oil, will not happen, folks. The only way, once again, please hear me out on this. This might be a test question. The only way to get moisture out of POE oil is with a filter dryer. Every time you open up a refrigerant system containing 410A refrigerant, you must change out a filter dryer as part of the process. Okay, here's a chart that basically shows the contaminants and the contaminant levels. Okay, this is found on page 238 of your textbook, the maximum contaminant level of recycled refrigerants in the same owner's equipment. So basically, you're going to have your acid content, your moisture, non-condensables, high boiling residues, chlorides, particulates, other refrigerants. These are the maximums that we can not exceed when we're utilizing that same refrigerant, reintroducing it back into the system. Now, I might point out, you're not going to have the ability in the field to test the refrigerant that you pull out. Okay, they do make identifier type electronic machines so you can identify what type of refrigerant it is. But as far as identifying all this, this is typically done in a laboratory environment only. This is presented just to show you what is going to happen. Okay, here on this chart, this is going to show boiling points. And I believe this chart can be found. Hold on one second. Okay, this chart can be found on page 226 of your textbook under Unit 9, and this is figure 9.9. This is a list of some known CFC, HCFC, HFC, HC, or HFO, and natural refrigerants with their safety classifications. Typically, these letter followed by a number is going to indicate the flammability of these different refrigerants, okay? Notice that the A1s are pretty much very safe. Once you go to B, now you have a little bit of more of a flammability standard. Now look what propane is, A3. So these refrigerants are categorized based on the flammability. Carbon dioxide is only A1, no problem there. Okay, R507 alpha, A1. HFOs typically are going to show up in the A3 column. As an example, R441 alpha, that's going to show up as an A3. R290, which is propane, it'll show up as an A3. And R1234YF, that shows as an A2L. I'm not sure what the L means, but this is going to show the flammability standard. Now, it even gets a little bit more interesting here. If you have a B classification here, so you have an A and you have a B classification. Okay, so just be aware. This chart here basically is going to indicate the flammability as well as the toxicity of these different refrigerants as well as the boiling points. Okay, here we have an illustration showing the different recovery cylinders. These recovery cylinders, notice they always have what they call a predominantly gray body with a yellow top. Typically, the bottles that you will be working with is 30-pound, 50-pound. These are what I work with all the time. Once you get to these large bottles, they become a transportation issue. Sometimes you have to use forklifts, chain falls, that kind of thing. Typically, you can take and carry these things up a ladder, up onto the roof, that sort of thing. These are easily transportable, where these are a little bit more challenging. This is an illustration on page 219 of your textbook showing the greenhouse gases in the tropospheric absorbing, refracting, and reflecting infrared radiation given off by the Earth. This causes the greenhouse effect, or what we call global warming or climate change. So basically, the greenhouse gases get trapped, infrared radiation being trapped here. And of course, the net result is we have warmer temperatures down here at the in our atmosphere. This is your chemical composition, which basically is on page 220. This is going to show your methane content as well as your ethane content of the refrigerant. Most refrigerants originate from methane and ethane molecules. Both molecules are hydrocarbons. Okay, we talked earlier in my lecture. This is an example of a Whirlpool bag. It's a plastic bag that is designed to hold refrigerant charge from the refrigerator. The bag can be transported to a shop where the refrigerant may be transferred to a recovery storage cylinder. I have personally not seen one of these bags in active use. I prefer the use of a recovery cylinder and a recovery machine. These bags are a little bit, I'm not familiar with the technology behind it. I think it was developed to make servicing small appliances and residential applications more simple. Typically, we're dealing with less than 1 pound of refrigerant in these machines. And for that reason alone, we can utilize this plastic bag. Okay, here we have an ozone molecule, a standard oxygen molecule. And basically, you're going to see this illustration 9.2 on page 218 of your textbook under Unit 9. Here you're also going to see under 9.3 in the same page, the breaking up of ozone molecule by ultraviolet radiation. We talked about the different atmospheric regions of the Earth. Basically, we are very concerned about the Tropospheric region, 7 miles, ground to 7 miles up, and then the stratospheric region, 7 to 30 miles. Here's where our UV shield is taking place to insulate us from the damaging effect of the ultraviolet radiation, which comes from the sun. Notice this is a situation where we have a relief valve. I will find the page that this is located on, so you can just take and I want to give you some information. This is on page 235 of your text. This is a dual pressure relief valve installed in parallel. And basically what happens here is these relief valves will take and vent this refrigerant to the atmosphere. Okay, if these relief valves lift, and if you got 1,000 pounds of refrigerant in here, all that refrigerant is going to go bye-bye. By code, you have to have a relief valve mechanism to relieve the refrigerant out in the event that this is exposed to fire, sudden heat, something like that. Basically, these relief valves will vent out the refrigerant to the outside of the building. Now, the problem is if you vent out 1,000 pounds of refrigerant, this has to be reported to the EPA immediately, hazmat people, and they have to be made aware. And basically, you just can't take and dump this refrigerant into another cylinder. By code, these are going to go to the is basically a vent pipe, similar to a vent pipe on a sewer system in your house or a building. And this refrigerant will get vented out to the atmosphere. This is a uniform mechanical code requirement. These are various types of recovery machines. The one that you'll see in our lab, I personally own one of these things here. This is a very, very good machine right here. These are okay. I'll be honest with you. This one here in the center is made by Appian out of Colorado, a suburb of Denver, Colorado. These things are very well, they're bulletproof. They basically hold up extremely well. And the thing I love about this machine, it is rebuildable. So if you wear the internals out, they do make a rebuild kit for these things, and you can completely rebuild it. All parts are replaceable. Appian makes an excellent recovery machine, and you can tell it's lightweight, and it has a very large, it can also take liquid refrigerant without any trouble. One of the issues I've had with this machine over the years, if you do not recover properly, you can actually mess up these gauges. I've had to replace them because of improper recovery procedure not being followed. We will show you how to use these machines in the lab so that you operate them correctly. But these things will last for many, many years. This Appian, this is, I believe it's a twin cylinder recovery machine, is very capable of recovering large amounts of refrigerant in a very short period of time. And of course, you got your plug, 115 volts. Excellent product. I love it. I endorse it. Works very well. On top of your recovery cylinders, you're going to find this information, the DOT stamp, the manufacturer, and it is also going to give you the TW, which is the tare weight of this bottle, and then it's also going to give you the WC, which is water, basically the maximum amount of water that this cylinder can hold. The thing that's very important is this tare weight. This is the cylinder when it is empty. Then here is the date when the cylinder is manufactured. These cylinders have to be taken out every 5 years and recertified. If you have old recovery cylinders that's been sitting around, chances are they are out of date. They should be swapped out for ones that are within the 5-year window of the recertification process. So these numbers are extremely important when you're recovering refrigerant. You have to know the tare weight, which is the empty weight of the bottle. And don't forget, if it's a 15-pound bottle, excuse me, if it's a 30-pound bottle or a 50-pound bottle, you're only allowed to fill this bottle maximum 80%. That is it. You do not go past 80%. You need 20% expansion capability on this cylinder. So as an example, if I have recovered R22, and this is a 30-pound bottle at 28 basically, if we have 28 pounds, if this bottle sits empty. Now, can we put in 30 pounds? No, we cannot. We can put in 80% of 30 pounds. So what is 80% of 30 pounds? Any clue? No clue? Okay, let's do the math here. So let's just take 30 pounds times 80%, 24 pounds. So we can put 24 pounds of liquid refrigerant, in this case R22, into this. So if you take 28, let's just use 28 as the tare weight of the bottle. We can add 24 pounds of refrigerant. So once we reach 24 pounds above that number, you have to cut off the recovery process and transfer it to another bottle. That'll still give us about 20% of the bottle for the refrigerant to expand and contract without blowing the relief valve. Now, I need to add a disclaimer here so you're aware of this. One of the major problems that we have today, and I cannot emphasize this enough, one of the problems that we have today is simply this. There are manufacturers of cylinders, or there are people that take and manufacture these cylinders. They don't have the DOT information on there. If you go to a swap meet, or if you go to a place and you look at a recovery bottle, which appears to be brand new, you do not see the stamping marks on these bottles, do not, and I repeat, do not purchase that bottle, because that bottle is a bogus bottle. It's probably a propane bottle that has been painted over and somebody's trying to make a quick buck. If you don't see these stamp marks on here, avoid using this bottle. I had a situation where I purchased a bottle from an offer-up customer, and it turned out to haunt me because these stamp marks were not in there, even though I knew the recovery limits, and basically I ended up losing half of the refrigerant into the atmosphere because of faulty equipment. So once again, these marks do not appear. Don't even purchase the bottle. Stay away from it. On some recovery bottles, you have the ability, they have a float switch that is tied in an auxiliary pipe plug port, and there's a communicating cable that is connected to your recovery machine, which will automatically shut the machine down once this float reaches the 80% capacity, so you don't have to take away the bottle. I have used these, but there's very few recovery machines that actually employ this process, but they are out there. They basically make the recovery process, I hate to use the term idiot proof, but that is the idea behind it. But you're not going to see this very often. Typically, you're going to just purchase the cylinder, and then you're going to take and use scales. And I might add, do not use a bathroom scale. Use an accurate refrigerant scale, such as Field Piece, JB makes one. There's several other manufacturers out there, but you need to get a quality product. Do not use anything else. There's a Yellow Jacket recovery machine. I believe this is a recycling machine. Let me find the page. Yeah, this is on page 239. This is a recovery and recycling machine. This has the ability to take and clean up the refrigerant as well as recovery. As you notice, it's a large, bulky machine. I doubt if you guys are going to utilize a machine like this for residential work. If you are, you're going to have to run long hoses up on the roof. That's a guarantee. Here we have a refractometer, and basically what this device is designed to do is to take an oil sample from the refrigerant oil that is circulating in the system. This will tell us what it actually tells us several different things. It's not a cheap instrument. It works very well. Let me call your attention to what it is here in just a minute. But this one here is made by New Calgon. I've seen these. I have not personally used one. This is a device which is available. It basically tells you the percentage of what type of oil is circulating in the system. So in other words, if you don't have POE oil and you're going to change that system to POE, you would use this refractometer type device in order to take an oil sample to see if there's enough of the new oil in the system to make making a refrigerant change doable. Let's see if I can find that thing. I haven't found it just yet. Well, here it is. On page 236 of Unit 9, figure 9.17, this is a refractometer used in the field for checking the percentage of residual oil left in the system. So in other words, you're changing from mineral oil to POE. This is the instrument that you will use. Okay, you have this chart here, basically required levels of evacuation for air conditioning. This is basically when you're using recovering equipment, you're not going to find anything hardly out there as manufactured before November 15th, 1993. I don't believe this is in the current EPA Section 608 of the Clean Air Act exam. This is the machinery that is what you're going to be utilizing after 1993. The magic number that you guys need to remember right here is 10 inches of vacuum. 10 inches of vacuum here, medium pressure, 10 inches. And if you go to an isolated refrigerant charge of 200 pounds or more, then you have to go to 15. So these are the numbers you need to be concerned with as far as your recovery machine. If your recovery machine does not achieve 10 inches of vacuum, that means your unit's worn out and needs to be rebuilt. Same way if you're recovering very low pressure appliance refrigerants, and typically they have anywhere from 6 to 1,000 pounds of more of refrigerant. They will utilize a water cooling mechanism in order to keep the machine operable. But notice that their vacuum level has to be 15 inches versus 10. Okay, basically, there's a chart here that shows the temperature, shows the UV radiation, ozone molecule, the heat generated. I believe we talked about this in the earlier lecture. But for your information, we can find this picture. I believe it is located. Okay, this is, let's see here. This is page 219 of unit 9.4. This is the heat generated from the breakup of the ozone molecules. Okay, here is a chart basically showing the appropriate lubricants for these refrigerants that are utilized here. This chart is also in your textbook if you care to refer to it. Typically, like I said, most new equipment today is all going to have POE oil and compressors, regardless of the refrigerant being used. This chart is figure 9.19, and it's found on page 236 of your textbook, and it gives you the types of oils that are compatible with the refrigerant. Obviously, R22 is mineral oil. You go to 410A, that is going to be, let's see if we can find it here. Okay, 410A, that's POE oil. So basically, these are the lubricants on this side, appropriate lubricants on this side. Take a minute to study this. Hopefully you've now seen these different refrigerants require, they can use different oils with the compressor. I doubt if you're going to see mineral oil. You're going to see alkyl benzene a lot on the more recent compressors, but pretty much today, this is all POE. I don't care what you buy. Most of the manufacturers have adopted the POE. Just remember with POE oil, once moisture gets in to that oil, the only way to get the moisture out of that POE oil is by using filter dryers, which must be changed for any maintenance functions, such as fixing a refrigerant leak, such as changing out the equipment, changing out the evaporator, changing out the compressor. You need to put in a new filter dryer. End of discussion on that one. Okay, here's a super duper, I believe I saw this in the book earlier. This is a Robinair machine. Automotive air conditioning shops utilize a machine like this. I've seen them. I've never personally worked on one or used one. Obviously, in my line of work, I will use a small recovery machine that is easily transportable to the roof or to the job site without having some limitations. So this is found on page 243. This is a recovery recycling machine that's built by Robinair Corporation. Very, very expensive. We're looking at thousands of dollars. Notice that you also have a vacuum pump. Basically, this is a service center. You'll see these a lot utilized in automotive air conditioning systems. I doubt if you're going to take one of these things out to a job site and hook it up to a residential commercial system because of location access. You would have to use large hoses, things like that. Here we have some electrical components, and you may or may not be familiar with what these electrical components are. You'll find this on a small hermetic compressor. Hopefully this was covered under electrical. This is going to be found on page 227 of your text. This is an enclosed relay overload that you're going to find on your small hermetic compressors, like for refrigerators, ice machines, that kind of thing. Okay, here's a chart that shows the flammability standards, which are employed with refrigerants, and they're classified. And this is going to be on page 230 of your text. This is your ANSI ASHRAE standard 34/2013, and this is their safety classification of refrigerants. So this basically indicates the flammability, or I should say, this is going to be the flammability side, and this is going to be the toxicity. So A1, B1 typically are safest refrigerants. Now we go up to A2L, B2L. Now we have a flammability issue. We come up to A3, B3. Notice we have a high flammability issue. So we have a situation like, say, for propane or butane, we'd probably fall in this column right here. So down here in this footnote says A2L and B2L are lower flammability refrigerants with a maximum burning velocity of 10 cm/s, 3.9 inches. So bottom line is, under certain circumstances, if you're utilizing a A2L type refrigerant, you do have a flame characteristic. If you have a spark or something, if the refrigerant leaks out, in certain applications, you could have a situation where that refrigerant could catch fire, cause an explosion. I have not seen this happen, but you need to be aware of this. Okay, here we have an exploded view. I'm going to guess this is a recovery. Let's find out here. I know I saw the illustration here just a minute ago. This is going to be found on page 246 under Unit 9. And this is basically an oilless refrigerant recovery unit showing the motor, crankcase, piston, cylinder, cylinder head. So basically, this is what it looks like when it's all taken apart. Notice that we use no oil in the lubrication process of this particular refrigerant recovery pump. Okay, here we have an illustration that just shows wires for the control circuit. So basically what is going to happen here, if you have the float switch installed, when the liquid rises inside the cylinder, the ball will rise and open the switch. This may turn on a light, preferably stop the unit, prevent overfilling. So you have a situation for controlling how much refrigerant is going into the bottle so you don't overfill it. This just shows the electrical characteristics on how this is achieved. You're going to find this on figure 9.28, which is on page 244, and it shows how it'll prevent the bottle from overfilling. And of course, this is a yellow jacket version of a recovery machine that you can take with you to the job site, to the unit, up on the roof, that kind of thing. And we talked about this. So this is the end of our lecture here for Unit 9, Refrigerant, Oil Chemistry and Management.